Fertilizers are one of the most important innovations in human history. Without the advent of industrial fertilization, it's hard to imagine how we would support a planet with 8 billion people. And without fertilizers, the famines of the 20th century would have been horrible. We simply would not have been able to make enough food to feed a rapidly growing population. Fertilizers plus irrigation, mechanization, and the other components of the Green Revolution are the reason that we have the agricultural system that we have today, but there are also drawbacks. Fertilization and over-fertilization leads to water quality issues, leads to production of greenhouse gases, and it's energetically expensive, and it furthers the climate change problems that we're already addressing. So the future of agriculture is going to be a balance between the benefits that fertilizers provide and the drawbacks that come from the use and overuse of fertilizers. So we'll talk more about why we use fertilizers and how we can think about them maybe a little bit differently as we move forward. We'll start out this video by talking about how the concept of nutrient limitation applies to crops and exploring what this means for agricultural management. One of the most interesting stories of the 20th century is the production of nitrogen fertilizer and how it came to be. And so we'll go through that story and also briefly explore how the overuse of these fertilizers creates environmental problems. Lastly, we'll take a look at phosphorus and examine how these fertilizers are also produced and how they, like nitrogen fertilization, can also create environmental problems. It's really important to understand how nutrient limitation actually works before we look at how fertilizers are used to alleviate this limitation to plant growth. I think one of the best ways to think about nutrient limitation is actually at the molecular level, because the reality of limitation is most obvious when you think about how a plant assembles its tissues. Plants obtain carbon from atmospheric CO2, and through the process of photosynthesis, plants capture light energy from the sun and use this energy to convert the carbon contained in a carbon dioxide molecule into a 3 or 4 carbon simple sugar. Plants then take these sugars and build the other molecules that make up parts of the plant. In this assembly process, other nutrients are needed, and in fact are critical to the function of different molecules. Just as an example, the molecule that sits at the heart of the photosynthesis reaction contains a number of nitrogen atoms and would not function without these nitrogen building blocks. So limitation occurs when there's not enough of a particular element to build the molecules that a plant needs to function. As a rough estimate, most agricultural plants need somewhere around 1 nitrogen for every 10 carbons that they can obtain from the atmosphere. This nitrogen is brought into the plant through the roots and then via a set of complicated biochemical pathways assembled in the tissues that a plant needs to function. Limitation occurs when there isn't enough nitrogen to support this process. So imagine a circumstance where a plant has access to plenty of atmospheric CO2, plenty of water, plenty of phosphorus, potassium, and other essential elements, but not enough nitrogen. In this case, growth will slow or perhaps even stop because the nitrogen is unavailable to assemble these tissues. Nutrient limitation occurs in all ecosystems, but for a variety of reasons it's more intense in agricultural systems. If you imagine a forest or a grassland, the material that is taken up by the plant, including nitrogen or other elements, is eventually recycled back into the soil when leaves or grasses fall to the ground and are broken down by microorganisms. In the picture here you see an agricultural field in rural Tanzania, and there's not much left on this field. Here the maize plants were harvested, the corn was taken somewhere else for human consumption, and the corn stalks were used to feed livestock somewhere else. In this case, there's been a net removal of nitrogen and other elements from the field, leaving fewer nutrients behind after harvest. This is a fundamental component of all agricultural systems, and it's not an exaggeration to say that these nutrients must be replaced, or the land will eventually be unable to support plant growth. Now, there are many ways to reduce nutrient loss in agricultural systems, and many ways to help maintain the fertility of soils, but this fundamental constraint has to be addressed to keep an agricultural system in production. When we think about fertilizers, there are 2 primary types, but also a third category of things that we can do that affect nutrient availability in agricultural systems. First, there are industrial fertilizers that are produced through a chemical process or through mining. And second, there are organic fertilizers that are produced through the use of plant or animal byproducts. Lastly, there are a number of additional ways to change nutrient availability or inputs to fields through the use of specific plants that fix nitrogen or chemicals that modify soil acidity in ways that cause nutrients to be released from mineral structures. We'll walk through some of these examples in the next couple slides. We'll start by talking about nitrogen. And this is one of the most important innovations of the 20th century. Some people say, actually, that the process of industrial nitrogen fixation is single-handedly responsible for the lives of billions of people who would not otherwise have enough food to eat. Here's how that process works. Most of the atmosphere is made up of nitrogen gas, which is comprised of two nitrogen atoms, N2. This form of nitrogen is extremely stable and unreactive, and it cannot be used in this form directly by plants. And in fact, it's largely inert in the atmosphere. In 1909, a German chemist named Fritz Haber developed a process that combined nitrogen gas and hydrogen gas in a high-energy environment to produce ammonia, or NH3. Ammonia is extremely reactive, and it can be used by plants as a fertilizer in a slightly different form. This form of nitrogen is also the initial chemical that is used in the creation of nitrogen-based explosives like TNT. It's no coincidence that this reaction was developed on the eve of World War I. By 1913, the process was scaled for industrial production by Carl Bosch. And yes, the company Bosch is a distant descendant of the industrial consortium that was created early in the 20th century around these types of ideas. Both of these men won Nobel Prizes for their work, and Fritz Haber went on to do some initial work actually creating the chemical agent mustard gas that was used in World War I. For nitrogen, this reaction transformed agriculture because for the first time it was possible to create nitrogen fertilizers at a scale that could support rapidly growing agricultural production. There is no question that the agricultural yields of the 20th and the 21st century could not have occurred without this innovation. But this production also has occurred with great environmental impacts. If we look around today at the options that we have available to us for nitrogen fertilization, we have these industrial sources, which include a mix of ammonium and nitrate-based fertilizers that are readily available for agriculture use around the world. The drawbacks of these fertilizers are that they are often overapplied, and then some form of nitrogen is often lost to freshwater systems where it can create enormous pollution problems. The production and use of industrial nitrogen fertilizers also contribute substantially to climate change through the production of greenhouse gases, both from the fields after they're applied and then also in the production process itself. Organic fertilizers are made out of plant and animal materials. They release nitrogen more slowly, and so there tends to be less loss to surface water systems. And some forms, like manures, are readily available in most locations. In some locations, there are sociocultural barriers to application, and it can be challenging to maximize yields with organic fertilizers. Used inappropriately, these fertilizers can also create environmental issues, although typically not as much as the industrial forms. The last type of input that we should talk about is biological end fixation. This process occurs through microorganisms that are either in the soil or live in association with plants, and in particular beans, peas, groundnuts, clover, and alfalfa. The reaction that these microorganisms facilitate is listed here if you're interested. The drawbacks of biological end fixer use are relatively limited and mostly revolve around the requirement to plant specific crops that fix nitrogen, often in rotation with the main crop, something like maize, for example. This can reduce overall yields from the field, but can also help stabilize and improve agricultural field and soil fertility. Nitrogen is not the only fertilizer, and after nitrogen, phosphorus is often the second most limiting nutrient for agricultural systems. There's a lot to say about phosphorus, and enough to take up an entirely separate video. But very briefly here, I just want to note that phosphorus is mined from bedrock, and that the bedrock reserves are found in a very limited number of countries around the world. There is an ongoing debate about how much phosphorus there is left, and some people argue that there are only a few decades worth of phosphorus supply left, while others say they're hundreds of years. These are very difficult predictions to make, and the graph here shows a couple of different scenarios for the future of phosphorus use under a business as usual, or BAU case, or with reduced demand in agriculture. In these estimates, which I made, we have enough phosphorus to last until somewhere between 2100 and 2200. And if you want to look more closely at this figure, just pause the video and read through it in more detail. And there's also more information on this in the textbook, A Changing Planet. To summarize, nutrient limitation is often more intense in agricultural systems than it is in natural ecosystems. And this is because crop removal requires some kind of nutrient replacement. The nitrogen fertilizers are mostly produced through industrial processes, and the overuse of these fertilizers create both water pollution problems and accelerate climate change. Phosphorus fertilizers are produced mostly through mining, and the reserves that we have for phosphorus are finite, and they'll eventually run out. We didn't talk much about it in this video, but like nitrogen, phosphorus overuse causes major water quality problems in both freshwater and coastal settings. Our alternatives to industrial fertilizers are organic forms, or in the case of nitrogen, the end-fixing crop rotations that we talked about earlier.